Okay then. Hello everyone. So today we will be finishing off the computer hardware slides. So that means next class we will actually begin on Python code. And so this is where we left off from last time. So we went over some Boolean algebra basics using the OR and NOT logic gates, as well as the three other basic operations, XOR, NOR, and NAND, which can all be built from the basic operations. We learned that NAND was the most important one because it could be used to build both NOR and XOR. And the binary addition can be done with the AND and XOR gates. So as we move on, we're going to kind of learn how exactly the CPU can perform these binary calculations. So we kind of know the basic logic behind how it does it, but we don't quite understand the hardware behind it yet. Okay, so there are some switch or flip states. So we need to understand that the way the computer can recognize whether or not the value being sent through the CPU is 1 or 0 is either on or off. And so on, which is binary 1, to off, binary 0, would show that the value is going from 1 to 0. And same thing vice versa. We would have to flip these switches by hand. And we all know that the computer can't do that. So there are certain technologies that have been developed so the computer can flip its switches like that. So in the next couple of slides, we're going to be going over some of the basics. So we have a vacuum tube. So the vacuum tube is essentially an electrical switch which is controlled by digital signals from another circuit. So this does not require any hands. It's all controlled digitally. And so this is kind of on the right side. You can see this diagram. And so that is kind of what a vacuum tube would look like. So a quick explanation of this is, so essentially we have the current which travels around the loop over here. So it travels around this way, and so over here the negative or electrons will travel from this filament supply, which is essentially right over here, and so they will travel through this vacuum area, and then they will get attached to the anode. And so these are very technical terms, and you don't really need to completely understand it. This is kind of information on a if we were to go deeper into the computer hardware, this would be necessary. But since this is kind of a quick overview, this isn't something that's necessary to memorize. So we're just gonna kind of go through very brief explanation of these. So as you can see, these electrons travel through the anode, and so this anode essentially receives it, and so that's how these can travel through this vacuum over here. Next is known as a relay. So this is how a relay would look in real life. It's not too big, and so this is kind of what it looks like inside. And so a relay is essentially, it's similar to a vacuum tube in that it's also controlled from electrical digital signals. And so you can kind of see two separate circuits over here. So what happens is there's a switch, and so this switch can turn either on or off. And when the switch is turned on, then that means that there's this kind of magnet over here. And so this magnet will force this piece to attach. And so this is how this switch and this circuit can control this circuit over here, whether or not this lamp can turn on or off. And next we have a transistor. So a transistor is a TTL. That's abbreviation, and so it is also a switch controlled by other electrical digital signals. You can kind of see a pattern going here. All of these kind of switches are controlled by electrical digital signals, and so this is what a transistor would look like, and so this is kind of a diagram of it. So there's a lot of components going on over here, but essentially the transistor over here, it's this is where like the actual switching would occur, and so these transistors, they are made of silicon, and the reason for this is because it is a semiconductor, meaning that its conductivity depends on various elements, whether that be temperature or some other element that can be controlled. And so this brings up.
Okay, so this is bootstrapping. The term bootstrapping comes from the saying of to pull yourself up by your bootstraps, which means to do something with your own effort. What this means in the computer world is how you can have one circuit's output start or control another circuit. So it's kind of like pulling up another circuit from one separate circuit. So this multi-circuit control allows the creation of complex TLLs. And as Matthew said, TLLs can be used to make simple circuits such as binary addition adders and more complex circuits. So in addition to starting up simple circuits, bootstrapping is also used to initialize complex programs such as operating systems like Windows and Linux. For example, pressing your computer's on and off button to give power to the motherboard, which in turn runs a hard-coded executable to initialize the startup of the OS. That hard-coded part in the motherboard is the bootstrapping. So, further applications of TLLs. TLLs can be used to build arithmetic logic units, which are shortened to ALU. As the name suggests, ALUs perform arithmetic and logic. They are the building blocks of a CPU. Multi-bit ALUs are basically multiple ALUs combined together with some additional logic circuits. These allow for the creation of bigger circuits, which can allow you to make bigger calculations. So that's what I have here.
Just to kind of summarize what we kind of saw there. So basically, the transistors or the TTLs, so they can build logic gates, electronic circuits that implement the Boolean algebra that we learned last class. And so with these new Boolean logic gates, we can perform these like binary addition electronically in the CPU. So here we kind of get into the specifics of an ALU. So here we're looking at a 1-bit ALU cell, and so this means that it can carry add, and, or OR. So these are kind of like the three different things that an ALU cell can encode. And so here we can see the idea of a full ladder, which we went over last class, and so we can also see the three different ALU cells over here. So the 1-bit ALU and the 4 operations. So the 1-bit ALU can compute a single-digit binary calculation, and so it can do addition, subtraction, multiplication, and division. And so you might wonder, well, if its basic operations include only and, or, and adding, then how can it do things like subtraction, multiplication, and division? Well, subtraction, multiplication, and division are essentially all they can all be built out of by addition. So subtraction is essentially just the addition of negation. Multiplication is the addition multiple times. And division is essentially just subtraction multiple times, or addition of multiple negated numbers. So this gets us into the multi-bit ALU. So I understand that it can be a little confusing because each ALU bit can, although it only has these kind of three basic calculations, can perform much more. So here we look at the 32 and 64-bit ALUs. So these are known as multi-digit binary calculations. So it's similar to, instead of just performing 1 plus 1, we go ahead and we go into like 30,000 plus like 20,000. So there's many more digits that we have to consider, and so there's kind of more ALU bits that are used in this calculation. And so this is kind of, you can kind of see in the name, so there's the 32-bit and there's the 64-bit, and so that kind of tells you how many calculations this can perform at once. So here's kind of a diagram of how it would work. So you can see that we have all of these singular bits, and so all of these bits combined together would be 4 total bits. And so there's all these like variable names and stuff, but this is essentially how the data is fed into these individual bits, and then how they are either like summed or subtracted, multiplied, or divided, and then they all form the final sum, which is located right over here. And so this is where the input is, and this is the output. Okay, so we looked at the CPU before, and so now that we have all this knowledge, we can kind of come back to it and see like how much more we understand of it. So we understand that there's the ALU, there's the control unit, and there's the cache. So you probably haven't heard of what a cache is before. And so essentially what a cache is, it's a storage. So even though this processor, the CPU itself, it is used to perform all of these calculations, it still needs some place in order to store its information, because in order for it to complete the calculations, it needs to take the input data and be able to release the output data. And so no matter how small this storage is, there still needs to be one in existence. So that's where the cache is. Now we've already gone over the ALU and the control unit. So the ALU is kind of how the calculations are all performed, from the single bit all the way to the 32 and 64 bits. And so these will vary from CPU to CPU based on its capabilities. It can have more ALU bits, it can have less. And there's also the control unit. So we can kind of look at this diagram and think about how this CPU would kind of work. So now that we've had a little time to think about it, so this will kind of wrap it up for us for this computer hardware. I know the information here is kind of daunting. There's a lot of stuff that we kind of learned today. This is all kind of extra stuff. It's not something that you would necessarily need to know going into programming, but it can certainly be helpful when going over your programs and kind of really understanding how your computer can actually process the information that you just handed to it. With that, we can kind of go into slightly more detail into how the bootstrapping can work. Alright, so this is we're gonna go into slightly more detail with bootstrapping. There's really not much to it. So essentially, bootstrapping describes the process of how the circuit output can control another circuit. So as David had said before, this is used in all of the switches that we learned about, whether it be like the vacuum tube or something like that. So this is very important, and it's kind of the basis of how we can understand how the ALU works. So you can kind of take your time to read over this. And we move on to complex bootstrapping. So this complex bootstrapping, it can also be used to kind of initialize a lot of complex programs, because many times, say you turn on your computer, uh, turning on that computer isn't necessarily a direct translation to booting up the operating system, or like say turning on some of your programs that your computer needs to run, or previous programs that were on your computer that need to kind of restart. And so the bootstrapping essentially allows a single press of a button to initialize an entire complex of programs. So it can initialize like multiple at once rather than just using one at a time.
So, as I was mentioned before, there are a lot more uses of TLLs, and then they can be used to make the ALUs that I mentioned before, which again are the building blocks of a CPU. CPUs also have ALUs are also combined together to make multi-bit ALUs, which I said before allow for even bigger circuits to add or subtract bigger numbers.
That kind of wraps up our complex lesson on things like the ALUs and the TLLs. So what we're going to do is we're actually going to go back to the very beginning and kind of cover over everything that we've learned, make sure that we've got a solid base. Alright, so here we have the computer anatomy. So as we learned before, the anatomy consists of the CPU, the motherboard, the heatsink, along with the two memories, the RAM, which is the random access memory, and the hard drive, which we learned can be either HDD or SSD. We expansion slots. This is for your USB ports, anything else that you kind of need for your input output for your computer. And finally, we have the power supply, because every single electronic unit needs some sort of power. So we learned that the CPU and the memory are the most important parts of the computer. And so the CPU is kind of like the brain of the computer. It computes all of our binary calculations, and the memory kind of stores all the data, whether this be kind of the RAM memory or the the hard drive. Both of them store all the information inside your computer. So here we have the auxiliary. So the auxiliary includes the secondary storage, the I/O or input output, and the communication devices. These are kind of necessary for you to kind of actively interact with your computer. And so here we get into more detail with the main components. So the CPU is essentially just fetching the data and the instructions and performing whatever you tell it to do, except it can only do it in binary, as we learned the ALU bits. And next we have the memory. So the memory, this is the temporary storage, so this is not the hard drive but the RAM. And so this is a temporary storage for instructions. As we learned, there's the opcode and the operands, which is the instructions on the data, which is loaded from the hard drive. And so the hard drive is the permanent storage of the computer, and it's stored in a file system. And this file system is kind of what you see when you open up File Explorer and you kind of look for the files that you stored or some information that you want to grab. So we know that the computer is an electrical system, a very complicated one, and essentially it's just performing numerous binary calculations at once. So it's just performing a lot of kind of brute math, I guess. So we learned about an electrical circuit, how the atoms, the electrons, can move throughout the circuit, and the electrons kind of complete the circuit in order for the power to go around the entire electrical circuit. And so we learned that conductors are great for the electrons traveling through them, whereas there are things like semiconductors which can be used to control the conductivity. And finally, we learned that the electrons kind of flow like dominoes, in where there's the electrons kind of bump each other. So each electron doesn't kind of flow through the entire thing, but rather it bumps the electron next to it, and that electron kind of bumps the one next to that. Next, we learned that there's the two states of the electrical circuit, where there's on and off. We learned that on represents 1 in binary and off represents 0. And finally, this is kind of a chapter summary of what we've learned so far. So this chapter summary includes how we learned about how the electrical circuit has the states of on and off. The computer is just a very, very big and a complicated electrical circuit, and that the discrete states can be used to represent the data in form of digital signals. And so that moved us on to signals. So signals are essentially any gesture or action that is used to tell someone any information or instructions. And this was, we learned about Morse code, and the two different states are signal durations. And so this was the chart that we kind of saw before. Alright, next is digital signals. So digital signals is essentially a continuous stream of alternating ones and zeros. So here we kind of see the 8 bits, or the 1 byte, in action. And so we calculated this in, I believe, our first class. And so this represents a binary number. And this binary number, it can also be a character. And so we learned how to calculate in binary, just as we calculated calculations in base 10 or base 16. And we learned about how a byte is a group of 8 bits, and the memory is essentially just a long sequence of bytes. And here we have the ASCII table. So I'll just kind of leave this here for you guys to look at for a second. And so it essentially contains a total of 128 different characters, and each character is numbered between 0 and 127. and so the answer was 76, or the capital letter L. Next we have the opcode, or the operation code. This is kind of the instructions, and so we learned this kind of a specific example of 0x10, or add with carry. And so add with carry is essentially a binary operation, and it tells us that we need to add and include the carry in. So to kind of conclude this short bit, we learned about the opcode and operands, the instructions and the data processed by the CPU. So this data can be in either numeric, character, or Boolean form. And so everything processed by the CPU is translated into binary form. And so this is called machine code. Finally, we kind of talked about binary addition. So binary addition is the only calculation that the computer can process, and so it does this in the form of digital signals. And before we get into the Boolean algebra stuff, we saw that we could kind of perform this binary calculation ourselves. How we can carry just like if it was base 10, instead in binary form, because there's only 0 and 1s as digits. And now we move on to Boolean algebra. So Boolean algebra include all the things from and, or, and not, all the way to the more complicated ones like XOR, NOR, and NAND. And so we learned about the truth table, the different logics behind each one of these Boolean values, as well as all of the signals or signs. And so we saw these real life examples of them, where the safe deposit was kind of like an AND because you needed both keys. The home entrance was essentially an OR gate because any of the keys could unlock the house, and a whining kid would be a NOT gate because, well, you can't get past one. And here's a Boolean logic. Boolean logic being represented in a Venn diagram. So we can kind of see this AND over here, and so it's this shaded in part in the middle. We have OR over here, and so it can include either one of these two circles. We have NOR, which flips the value over here, and we have exclusive OR, where it includes everything but outside and the two overlapping parts. We then learned that NAND is going to be the most kind of important logic gate because it can be it can be used to build any other logic gate. So we kind of saw this example of XOR down below, and so this is how the NAND logic gate was built. And here is our example of binary Boolean logic and binary addition. So this was where we kind of saw the Boolean logic in action when we were trying to calculate this binary addition. So we saw that there were two places where we needed to use our Boolean logic. There was the actual adding over here, and so we know that this one used a XOR gate, and this carry logic over here using AND gates. And so that's kind of how we learned that binary addition's basis consists of XOR and AND. As we can see over here, this is kind of a basis of how the computer programming actually works. So we'll just take a little to kind of examine this. Alright. And then we learned about the half adder, and so the half adder was essentially just used to add 2 digits without taking into account of the carry in or the carry out. So that's how we saw the half adder work. And so this was kind of a truth table, how the half adder would actually work if we were to use it. So we see there's the sum and the carry. And so that brought us into the full adder. So the full adder was essentially, it would take into account both inputs and a carry in. And so the truth table below kind of shows how that would work. And just to kind of summarize, this is where we start off today. So Boolean algebra kind of defines the 3 basic Boolean operations, or, and not, and from those basic operations you can build more logic operations, and this includes exclusive or, NOR, and NAND. And as we went over, NAND is the most important one, and also that binary addition can be done with just the and XOR gates. So we'll kind of look at this a little more because this is very important. And so now we're gonna kind of move on. So I know you guys are probably very excited to kind of learn how to actually program in Python. And so the first step to that is going to be downloading Python, because without a proper IDE or a software where you can actually program it, it's kind of impossible to actually program in Python. So we're going to go here and scroll down. These are kind of the instructions, so you guys can kind of look over this yourself, but I'm gonna kind of do a run through of it for you guys, so I'll put it in the chat for you to see. Alright, so the first step is going to be downloading the Python through their website. So you're going to go to the Python website. So we're going to go to python.org, and so from python.org you can go to the downloads section of their website. So when you go into the website, you'll see it over here. So you can click on the latest Python 3.8.3. So you click on that and you see all these new features. You don't really need to look at that, and you can see more resources, but all you really need to do is you need to go down to here in files. And so in files you will see that there is a you want to in order for it to be the fastest possible, you want it to be executable. So essentially all you need to do is just click on it and it will do everything for you, kind of. So you can see that you have all these different file names over here. You can ignore all of these, so the help, the Mac, unless you're on a Mac, then you're going to need to use this. You don't need to know these two, but you can see that there's an embeddable zip file, so that means you need to do some extracting. We don't want to do that. So we have an executable and a web-based. So we don't want the web-based. We just want the executable installer right here. And so you can see that there's two executable installers. There's the regular Windows x86 and there's one a 64. So we're going to click on this one over here. And so we're going to wait for that to download. Alright. Let me change this. Alright. So you can see that, so unfortunately, since I already have this downloaded here, there's already this modify setup thing, so I'm not going to be able to show you anything past this point, but I can kind of explain it to you. So we're gonna go back to here. Alright, so so after you've kind of done that, then what you want to do is you want to make sure that you have the correct path selected. So essentially what a path is it's a way for your computer to fetch the program, and so in order for it to fetch the program, it needs to know where the program is located inside your computer. And so once you know kind of where you want the Python to be installed, usually it has a standard kind of installation path, and you just need to make sure it's not installed somewhere like you don't know. There are many guides that will kind of tell you how you can correctly select your path, and so you want to click on install now. And so this will start beginning the installation process, so it will add the program to wherever path you selected. So after you've kind of done that kind of installation process, what you're going to want to do is you're going to go to the command prompt. So we're going to open that up. So okay. So what you want to do is you want to click on Python Python space dash version, and so this will return the Python version that you're on. So I installed this before, so I'm gonna be kind of a little behind in the versioning, but it kind of shows that I'm Python version 3.7.3. Now it's fine if you're on 3.8.3. There's no major changes or anything. So as long as this doesn't say something too old, I suppose you're going to be fine with this course. And so now that you have kind of checked your versioning, you've successfully downloaded Python, then we can move on to actually writing something in the Python terminal or the Python IDE. So what we're going to do is we're going to open up Python. And so this is kind of your shell over here. So the shell is not going to be where you're actually going to program, because in the shell, if you were to type the basic command print hello world, it will kind of automatically return the value here. However, it's not ideal in that once you kind of run this, it's unretrievable, so you can't run it again. And so that's why instead of doing everything that that we learned in a shell, what we're actually going to do is we're going to click on new file. And so after we click on new file, you kind of see this blank screen over here. So, or oh, you guys can't see that. There. So you kind of see this blank screen over here. So before you guys kind of saw the text at the top and like kind of these like arrows over here on the side. So this blank screen kind of indicates that you're actually in like a separate file, and you can save it into whatever you wish to if you were to want to kind of reuse that code. Now, the useful thing about the shell is that you can kind of run quick commands. So if you wanted to test out if you could print something or anything quick really that you don't really mind saving or anything like that. And but for all of the kind of projects that we're going to go over, anything that you want to keep, want to be able to check later, you're always going to want to go into a new file. So just to remind you, all you need to do is click on File and then New File over here. Now, after you've written something in here, say you were to go to print hello world, you're probably wondering, how do we run it? How do we see if this code works or not? So you're going to go to run over here, and so you have these three options over here. You have Python shell, check module, and run module. So all you're going to need to do is press run module, and so you can see it says it must be saved. So we're not going to actually save it because I don't know where the file is at right now. But what you're going to do is it's going to kind of open up File Explorer, and you're going to click on where you want to save it. I would suggest making a new Python folder for you to store everything that you were to learn in this class. And after you've done that, you need to make sure you name it something that you can remember when you want to come back to it later. And after you've done that, then now that file is kind of permanently stored in your hard drive, so you can open it whenever you want, as long as you know where the location was. And so now that you know that, you can kind of start programming. So that will wrap up our class for today. If you have any questions, please ask it in the chat. Does not look like there are any questions. Thank you everyone for watching. And I guess we'll see you on Friday. If you have any questions, then make sure you go to the office hours. Thank you.